Okay, today we're going to be going over the final presentation or the final project, and this is the video report of it. I'm going to focus in on train my models. One thing that I added in for all of the models, including the autoencoder, so the CNN Scratch, CNN VGG16, and the autoencoder, was this early stop and reduced learning rate. And that seemed to impact, especially the CNN. I didn't get to test the autoencoder extensively enough to see exactly how it impacted the autoencoder, but I used it because it had such a positive impact on the CNN models. And so what that does is it just makes sure that that the validation accuracy is at least increasing by 0.003 every 7 epochs. And if it hasn't done that, then it stops early. But before it gets to that point, every 3 epochs, it also checks to see if it's increased by 0.003. And if it hasn't, then it decreases the learning rate by a factor by 50%. So, and then it keeps decreasing until it reaches its minimum, which is 1e minus 6. So, so it gives it a chance to reduce and correct and start improving before it early stops. And then I can also set the epochs to epoch 50, and it's not going to take 50 epochs for every time. But if it does happen to keep improving until that time, it also doesn't stop it early and miss the opportunity for it to improve. Okay, so then the rest of this is recording the top performers and the bottom performers, which I record. This is what generates these figures. Here is the top performers and the bottom performers, and I collect them in the train my models function. And so I also added a KL score, which is just sort of a basic score that is an attempt to combine a lot of different scores. And I gave a lot of weight to the best score possible, or the best score that was achieved of all the epochs, since this component of this project is a competition. So I weighted that heavier for that reason. Okay, so now save, load, print, general. Okay, so here we are generating the random parameters. And so if we go down here and look at our parameter grids, it's going to take these parameter grids and generate as many combinations as we specify using these parameter grids. And I tried to keep it the same between the CNN Scratch and VGG16. So that it sort of had the same range of accessible, but I did change a couple of things. I also, I believe I put, did more combos for VGG16 than Scratch. So the winner overall was VGG16. So it's important to bear in mind that I did have a larger search net or domain for the hyperparameters for that particular model. So that may have impacted or biased the scores. But okay, so all right. Anything worth noting here? Okay, so going down to the autoencoder, this is where things got really messy. And this is just a lot of code of me running through things, trying to test things out and failing, and then trying new things. And then, it's just a mess down here. So I was in a hurry. and that's obvious because I'm late with this assignment. So let's see, what's a good thing to note? So here we're corrupting our images and adding noise. And here's our autoencoder class. We've got the encoder and the decoder, and we've got convolutional layers for the image data, and in both our encoder and decoder. And so this is a display images function. We've got our autoencoder classifier class, which uses one dense layer before the final classification, and it also uses 0.35 dropout. One thing that I do want to talk about, just because it's not really that apparent how hard I worked on it in the report, is the other metrics. It was asked that we get some images that were misclassified by all of the models, and I don't know why, but I could not get that figured out. I couldn't get it figured out with the CSV info, so that was provided. So I ended up doing a workaround, tried a bunch of different things, and finally got to this, and was able to print out the true label and the class that was predicted by each model. And I did this with by storing all of these images into a data frame, which was a lot, so I could only store a limited amount. So I just focused in on one smaller category. But anyway, I got some misclassified images that were across all of the data. One thing that was really interesting, okay, so just let me, before I get there, go through the report here. So we've got our different scores that we want to look at. Here's the list of hyperparameters that were used in the parameter grids. And, excuse me. And so we've got our top models. Our dropout rates for our top models tended to sort of hover around these middle ranges. Of course, the bottom models tended to have similar dropout rates. So it's hard to really isolate one hyperparameter over another. It seems more about how they all work together. Here is this is the infrared data set tested on the models, and then the color images that were tested on the models. As you can see, I got pretty good scores for the top models. The top was 0.95 validation score for the CNN Scratch model, and thanks to that learning rate curve that was adjusted along the way, that really squeezed out some extra top values. The RGB wasn't much different than the infrared at 0.953 for for the top RGB CNN scratch model. And then the infrared VGG16 got all the way up to 0.971 for validation accuracy. And training accuracy got up to 100%, which oftentimes is a strong giveaway that there's going to be overfitting, but in this case, the overfitting was still low. So it still mitigated overfitting even though it reached 100% training accuracy. So it was able to take what it learned and apply it pretty well to unseen data. The KL score was high, one of the highest for, if not the highest KL score for all models. And then the RGB VGG16 was identical in the top score. Oh, where did it go? In the 0.971 accuracy, but the validation loss was much lower. The validation loss was 0.476 for no. Sorry, I'm getting turned around here. 0.256 and 0.274. Okay, so not that much different. I saw this. Okay. So moving down here to the autoencoder, here are the noisy images that were generated, and then here are the denoised images that were generated. And as you can see, they're smoother and look kind of blurry, but that's because the noise has been reduced, which kind of adds some sharpness to it. Pretty good representations here, I think. And then here it is for the color images, which took a lot longer. And I didn't post it here, and I probably should have, but I changed something very simple. I just changed one thing, which was, so I had taken off these convolutional layers because I was worried about it taking too much time. But when I got the results back, the images that were produced were just not even, they were basically just this kind of the shape of these legs here, and then everything else was black. And then like over here on these were just black images with maybe like weird colored things in here somewhere, and it didn't really make a lot of sense. So I went back in and I added these convolutional layers back in, and voila, these images came out. So that was pretty important for creating those images. Okay, so here we have some random images that were classified. So we've got this one and this one are the only two that are represented that are misclassified. And this makes sense. I don't know what that is. Do you know what that is? It's a blob. And this is remarkable to me. I have no idea. This maybe it just got lucky, but I don't know how it identified that as a person, especially when you look at other misclassifications like this one and this one. But I'm not 100% certain that this group of images, and that was part of my struggle with the identification of the same images. I don't think these are correct. So, and I have gone around in circles so many times that I couldn't even tell you why at this point, but I'm pretty sure these are not correct. It's been a long time ago since that was the first round of code, and after going back through it, I feel confident that the indexes got all mixed up for these. So these are definitely correct, and you can tell that they're correct, that these were misclassified. These don't make a lot of sense in some cases. This doesn't make sense. These don't make sense. The rest of them could make sense. But, okay. So, all right. So now we've got a side-by-side comparison of the top models for each architecture. And one thing that's notable about the auto class is that it starts off, it doesn't have this shroop sort of learning curve. It just starts straight away right at the almost at where it ends. You know, it improves just ever so slightly. So with this big gap here, I'm fairly confident that there are hyperparameters that would enhance these scores and narrow this gap in the same way that these were discovered. But basically we've got the CNN VGG16 coming out reigning supreme on pretty much it won on every score that was measured except for its ability to the gap, which actually here, this gap, yeah, so this gap here is smaller, and its validation loss is lower, and so in some ways it might be able to generalize a little better or be a little less overfit, but that's about the only thing that the Scratch model or any of the models sort of had above and beyond the CNN VGG16 model. So in that pattern extends all the way down into the confusion matrix. The F1 score and the A1 score are all higher for the VGG16 top model. So looking at these and I'm gone way over on time, so I have to wrap it up, but looking at these confusion matrices is pretty interesting, because here you can really break down how many times sign was mislabeled as light or person was mislabeled as light. And this is where you can really start to see the distinctions between the VGG16 model. See, person and light was only confused 5 times. Person and light was confused 32 times here, and it was confused 28 times for the Scratch model. And then they all confused sign and light more often, which makes sense just intuitively, because the human eye would probably have the same difficulty. So one place that the VGG16 struggled with that the other ones didn't struggle with as much is identifying bus as truck. Here it's only 2, and here it's only 7. So, but overall, if you just look at zoom out and just look at the color patterns. That's what's so great about the confusion matrix, is that you can really see visually what's happening, and how much confusion there is around the matrix when you want there to be just a solid line across the diagonal. Okay, I think that's enough. Thank you very much.